When we have two functions, we can combine them together in a few ways. We can add, subtract, multiply, and divide, and then we'll do composition here in a minute. But if we have two formulas, f of x, I picked example 8 here, f of x is 1 over x minus 4, g of x is 1 over 6 minus x. We can add, subtract, and multiply those to get new functions. So if I wanted f plus g, at its most basic, I just add the two formulas together. I have 1 over x minus 4 plus 1 over 6 minus x. That's my new function, the sum, f plus g. I could get a common denominator if I wanted to, but I'm just going to leave them this way, 1 over x minus 4 plus 1 over 6 minus x. Definitely if you get common terms, like if I wind up with, say, like a 2x plus 3x, I would go ahead and add things like that together. But in this case, I don't think it's worth the trouble of getting the common denominator. I'm just going to leave them like that. Same thing with subtraction. If I subtract the two, I get 1 over x minus 4 minus 1 over 6 minus x, where I could get a common denominator if I wanted to, but I'm not going to. And then multiply them. Depends on what I have as to what I might do when I multiply them, but here we have multiplying the two fractions. We can multiply the numerators and denominators, so we get a 1 on top, and then we have the product there of x minus 4 times 6 minus x. We could multiply that out if we wanted to, but actually usually in math, when you get more experience using these things with rational functions, often we want to figure out the points that are not in the domain, which are going to be asymptotes on the graph we'll talk about later. So it's actually probably more useful to have the denominator factored on that one. So I'm going to leave it like that, 1 over x minus 4 times 6 minus x. Division, I would definitely do a little simplification here because we have what's called a complex fraction. We have a fraction over a fraction. So if we do f divided by g, we have 1 over x minus 4, that whole fraction over the fraction 1 divided by 6 minus x. So instead of having the complex fraction, we can turn that into multiplication. We can divide by the reciprocal of the bottom one. So it's the same thing as 1 over x minus 4 times, flip the second one, 6 minus x over 1. Then we can multiply top and bottom and just get 6 minus x over x minus 4. So those are my examples of adding, subtracting, multiplying, and dividing with formulas. I forgot to do one with graphs. I do composition here in a minute, and I'll talk about it maybe in addition or multiplication or something with the graph in a second. So before we do that with graphs, I'm going to do composition with the formulas. So composition is when we put one function inside of another. We're going to do f of g and g of f in this example. So we need two functions. On number 12, we've got f of x is x squared plus 1, and g of x is square root of x plus 2. And I'm going to do composition. I've reminded you, you might see instead of the nested parentheses, you might see the composition symbol, the little, it's kind of like a little O. It's f of g. So this little O symbol, a little circle symbol. So that's f of g of x, which literally is nested parentheses f of g of x. The little circle gives us another way to write it. So whichever way I write it there, we're going to do f of g of x. The nested parentheses shows me I have g of x inside. I'm going to put that inside of f. So I take f's formula, x squared plus 1, and remove the input, and I input g's formula, square root of x plus 2. So there's f of g. We have the square root squared. I could go ahead and simplify and just get x plus 2 plus 1 or x plus 3. I made a little note there. Technically, when we do the composition, the domain, we would have to have x plus 2 greater than or equal to 0 or x greater than or equal to negative 2. So we can cancel and say it's x plus 3, but really it only is for x greater than or equal to negative 2. Otherwise, the square root part would give us imaginary numbers. If we did g of f, that'd be the opposite order. We would take g's formula, square root of x plus 2, and take x out and plug f's formula into it, which was x squared plus 1. And there we have under the square root now, x squared plus 1 plus 2. We could go ahead and say is the square root of x squared plus 3. Okay, so there's some examples of composition. Next, we're going to turn to graphs. So I didn't do an example of addition, multiplication, division, subtraction, but those are actually pretty simple. You just use the y values. Say I want to do f plus g of 3 or f of 3 plus g of 3. I would just find those two values. F of 3 is 2, g of 3 is 4, and I would add those together. 2 plus 4 is 6. So f plus g of 4, f plus g of 3. I better type this one out for you. Okay, so here we go again. So an example, if I wanted to do addition, f plus g, if I want to take that function and evaluate it at 3, by definition it's f of 3 plus g of 3. I can find those values on the graph. At 3, f is 2. At 3, g is 4. So 2 plus 4 is 6. If I wanted to multiply, f times g of 3 would be 2 times 4, and I'd get 8. So I just do the operation with the two y values. Composition is a little more involved because you have to evaluate one function and then go to the next. So I'm going to do all four of these. We're going to do f of g of 3 first. So again, you could see that written either way with the little circle or with the parentheses, but both of those I would read as f of g of 3. So the first thing I would do is find g of 3 on the inside. And at 3, g is 4. And then g of 3 is 4, so now I need to do f of 4. So g of 3 is equal to 4. So we have f of 4. F of 4 is 0, if I look at that graph. Okay. So I take my x value and I evaluate the first function and then use that output as the input for the second function. So if we wanted to do f of g of 1, the first thing we would do is g of 1. G of 1 is 3, and then we're going to take 3 as our input, and f of 3 is 2. So g of 1 is 3, and then f of 3 is 2. A couple more here. G of f of 1, the other order here. Now we're going to do g of f of 1. So f of 1, first of all, would be 3, and then g of 3 is 4. So f of 1 is 3, g of 3 is 4. And then one more, g of f of 0. So f of 0 would be 4, and then g of 4 is 5. So f of 0 is 4, g of 4 is 5. So that's how we do composition numerically if we have graphs or tables to get those y values.